Good morning, everyone. So we have done Newtonian mechanics and Lagrangian mechanics in brief. Now we move on to relativity, and we discuss a few topics such as sending signals and emergence of the speed of light to be the ultimate speed that one can achieve. Then we will talk about Galilean transformation, different frames of reference, in particular the inertial frames, and why Galilean relativity breaks down. We will talk about Michelson-Morley experiment, which rules out the presence of a preferred frame of reference called as a ether frame. We will also talk about the postulates of special relativity, and finally we talk about length contraction and time dilation. So, we start with sending signals in space. So, it can be done with the say for example radio waves or electromagnetic waves, and that is the fastest mode of communication that one can achieve in space by sending signals through light. Okay. So, anything greater than the speed of light is not possible, which also emerges out of special theory of relativity. So, let us just talk about the frames of reference. Okay. And what we mean is the following, that suppose there is an artificial satellite which is circling the earth at say a speed of 18,000 meters per hour. Okay. So, the V by C that comes out as it's point 4 zeros and 27, whereas the speed of light, so this is for a satellite, and for sound V is equal to somewhere around 330 to 332 meters per second. This is in a vacuum. So, V by C comes out as 0.00001 and so on. So, these are some of the speeds that we are familiar with, very large speeds, and in real world, of course, it is possible to accelerate electrons which are by say about 1 MeV of energy. If you want to accelerate, or if you accelerate the electrons, then they reach a speed which is close to C, maybe 0.9988 C. This is for 1 mega electron volt, and now what happens is that if you accelerate it by say about 40 MeV, and then Newtonian physics says that this is going to be 1.9977 C. So, so this is the speed of the electron. So, this is for an electron, and this is accelerated by, or this is in particle accelerators. And it looks absolutely fine because you have used the equation of motion, and it gives 1.9977 C, and this is what Newtonian mechanics predicts. Uh, 1.9977 C. Okay. And there seem to be nothing wrong with this, but of course, we know that the ultimate speed by which signals travel, or by which anything that can travel, the maximum speed is that of speed of light. Okay. Newtonian mechanics does not distinguish between the speed of light. In fact, if you look at all of the discussion of Newtonian mechanics, it never has a real special space for the speed of light. So, it sort of predicts it just the way it predicts the speed of any particle. Okay. So, we are really worried about two important things while we talk about relativity, and these things are laws of mechanics and number 2, laws of electromagnetism. Okay. So, with this let us talk about both the frames of reference and that of Galilean transformation. So, we discuss what is called as an event. Okay. Say an event is anything that happens in space time. So, suppose an event happens in x, y, z and t. For example, suppose in some reference frame, okay, which is that could be a stationary reference frame, something happens with x equal to 1 meter. So, let me write that. So, x equal to 1 meter, y equal to 4 meters, z equal to say minus 2 meters and t equal to 5 seconds. And we write this event as 1, 4, minus 2 and 5 in some reference frame. Now, in another reference frame which is either stationary or moving, this event can still be represented by another x prime, y prime, z prime and t prime, where they are set of 4 numbers once again, but they have different values. For example, if a car is parked in a parking space and someone who is standing very close to the car observes this event of this car being parked, and he notes down this x, y, z and t, and another person who is probably standing 30 meters away, he also records these the data of x, y, z, and of course, time will be same because they are recording at the same time. So, this event of parking the car at 2 reference frames are represented by x, y, z and t, and x prime, y prime, z prime and t. Okay. So, is there an unambiguous description of event? What I mean is that all these reference frames, can they converge? So, is there one unambiguous description of the event which tells you that there is a need for a preferred reference frame? So, when we say a preferred reference frame, we usually mean what is called as a inertial frames. And by inertial frames, what we mean is that a frame of reference that is moving with respect to another frame of reference with constant velocity, either it is at rest or moving at a constant velocity with respect to a stationary frame. Okay. So, these are called inertial frames. For example, consider a sort of boy sitting on a stone on a field, say, and say for example, a satellite is really floating in outer space and it is not spinning, it is just simply floating in outer space. So, that way very strictly speaking, the boy stand or rather sitting on the stone would not be called as an inertial frame, because the earth is rotating. So, if there is a rotational motion, then there is an acceleration, and the acceleration really prohibits the boy who is stationary, who is sitting there, cannot be considered as a reference frame. But then we know that these acceleration is so slow that for all practical purpose anything that is stationary on earth can be considered as an inertial frame. Now, a car speeding or a train moving where its velocity is continuously increasing cannot be called as a inertial frame, and they are called non-inertial frames. So, inertial frame is one which moves with a constant speed with respect to stationary frame, or it is at rest with respect to the stationary frame, and a non-inertial frame is the one which accelerates with respect to a stationary frame. Okay. So, that is the definition of stationary or rather inertial frames. And in fact, STR deals with special theory of relativity, as it is called as. So, let me write that special theory of relativity, which was formulated by Einstein, and that deals with inertial frames. And in fact, the general theory of relativity deals with any kind of frame, including inertial and non-inertial. Okay. Let us talk about the Galilean relativity or Galilean transformation. So, there are two frames, okay, and these are moving with respect to one another, but with a constant speed. So, these are the two frames, and one can call this as S frame and S prime frame, where the S prime frame is moving with respect to the S frame with speed u. And we make matters a little simple by taking into account that this is the x axis and this is the y axis, and say this is the z axis. So, in principle this speed or rather the velocity of this S prime frame can be in any arbitrary direction, in which case it becomes a vector. But for simplicity and no loss of generality, we take this u to be moving along the x direction. And in addition, you can enforce other constraints, such as at t equal to 0, the two coordinate systems are their origins are at the same place, etc. Okay. So, suppose there is a point P, okay, which is say at a distance x prime from this, and so they are sort of aligned along this direction. So, there are these assumptions that we should write down. So, one assumption is that the origins of the coordinate system, and we write a CS coincide at t equal to 0. Two S prime moves along x axis with constant velocity u. Okay. So, these are the two assumptions that we make here, in which case x prime is clearly equal to x minus ut, y prime does not change and z prime does not change either. In classical physics there is no transformation of time, or in the Galilean relativity there is no transformation of time. So, t prime is equal to t. The interval of two events, consider there are two events P and Q, and they occur at Tp and Tq. So, say a projectile is taken off and then it probably bursts into different fragments. So, there is Tp for the first one and Tq for the second one, that is taking off is considered as Tp, and this other one is taken as when it bursts into different fragments is taken as Tq. And if you look at it from another reference frame, it is say Tp prime and Tq prime. Okay. So, this is in say for example S and this is in S prime, then T p minus T q is equal to T p prime minus T q prime. Okay. So, and also the distance between the 2 points, that also remains same. So, that is x say for example x p minus x q is equal to x p prime minus x q prime, where you can consider this p and q to be I can write it with different indices, probably that is less confusing. So, let us call it as x a and x b, x prime a and x prime b, where a and b are the two ends of a rod, and this rod is stationary in S and is moving with constant speed in with speed u in S prime. Okay. So, this is all what is known to us. So, x b prime, that is in the S prime frame, is x b minus v t u t b. That is because so if S prime is moving with respect to S with a speed u, S is moving with respect to S prime with a speed minus u. So, x b prime is x b minus u t b, whereas x a prime is equal to x a minus u t a. So, that gives x a prime minus x b prime is equal to x a minus x b, and that is u t b minus t a, and this being equal, we conclude that this is equal to x a minus x b. Okay. So, this is what we have said, that these are the transformation equations, and we again get this T b prime equal to T a prime if we do the inverse transformation between this x a and x a prime and x b and x b prime. Okay. So, the time interval and the space intervals are absolute in the Galilean transformation, that is, they are same in all inertial observers, or they are same for all inertial observers. And so, in the measurements of length and time of two different events, the relative velocity of the two frames, that does not come into picture. As you saw that neither in the length nor in time the speed u, which is the relative speed between the two frames, that does not come into picture. So, if we add, mass also remains invariant, that is, in addition to the length and time, the mass also remains invariant. What I mean by invariant is that the speed u does not enter into the transformation, that is, mass in frame A and mass in frame B, they are same. Then of course, we get the length, mass and time all remain invariant and independent of the relative speed of the two frames. Okay. So, this is a result that we get from Galilean relativity. Okay. So, how do the velocities add? The velocities would add as the velocities of the particles would be related by some u prime equal to u minus v and so on, and so this velocity in u prime. So, let me write it with a v here. So, this v prime v minus u. So, this is the velocity in s prime, and this is velocity of the particle in s, and this is the relative speed between, or relative velocity between the two frames. You should call it a velocity, we are writing it as a vector. So, these are same, and for the acceleration now we have a prime is equal to a, because you take this derivative of this equation that you see above, and with respect to t, because u is a constant, that is a constant speed. So, a prime becomes equal to a, which tells you that if I multiply the mass, which has already been taken to be an invariant. So, your f prime, which is equal to m a prime, that is equal to m a, that is equal to f. Okay. So, that tells us that the Newton's laws are invariant. So, in Galilean relativity, the Newton's laws are invariant, but this poses another problem, because so why Galilean relativity, let me write it as Galilean relativity breaks down. This is one of the questions that we asked to the front page itself, and one can really see that suppose there are two electrons are ejected in opposite directions from either from some nuclear reactions, or say from some radioactive atoms. In lab, so these atoms are at rest. In lab, and so the speed of one electron, say for example, with respect to another is 0.67 c. Okay. So, what is the speed of what is the sort of relative speed of one, and they are opposite directions, they are emitted in opposite directions. So, the speed of if you look at these two frames s and s prime, and think that this speed of the s frame, which where the electron is at rest, is 0.67 c, again in the negative x direction. So, your addition of velocities tells you that your u x and u x prime, that is the speeds of the particle or the electrons in the stationary frame or the s frame with respect to the s prime frame is u x prime, and now both of these is 0.67 c plus a 0.67 c, that makes it equal to 1.34 c. And since we know that there cannot be anything that is larger than the speed of light, or no speeds can be larger than speed of light. So, this is really an absurd result in special relativity. And that is not allowed, and we then need to sort of change the notions of these transformation equations, and they carry certain consequences of this this exercise. This says that a collision between two particles or two masses cannot really determine the relative velocity between the two frames. For example, say two tennis players are playing on a moving ship, which is the ship is cruising in calm water with a constant speed. Now, the two tennis players, by looking at the velocities of the balls that they hit towards each other, that cannot determine the speed of the ship. Okay. So, that is a simple thing, and we sort of if you look at any collision events, that collision events looking at this velocities of this before collision and after collision, one cannot determine the two relative velocity between the two reference frames. Okay. So, now it was for quite a while that it was thought that there is indeed one reference frame that is preferred over another, and this reference frame is called as a ether. Okay. And light actually moves through this preferred frame, and this would give rise to, and this preferred frame or the inertial frame has a certain velocity with respect to another frame which is completely at rest. And so, if light is moving through the ether, and then we should be able to detect the speed of ether. Now, since in those days when these experiments are being done, there was no direct way of presence of ether or the absence of ether or this preferred reference frame of reference was not available in those days. So, they had to do some measurements, indirect measurements, in order to detect the presence of ether, and this led to this famous experiment by Michelson and Morley. And we will discuss this experiment because this is quite important. Okay. So, just to put things in perspective, so this is the sun that we have, and this earth is moving around the sun. So, when it is here, its velocity is tangential to the orbit, and when it is here, the velocity is tangential to the orbit. And so, this is the position of the earth. So, this is a position of the earth, let us call it by E, and this is the position of the earth at the two extremities and so on. Okay. So, now let us try to see this how it comes. So, we will have to draw a neat diagram for that. So, that is a mirror. Let me finish this, then it will be clear. So, there is so there is a partially silvered mirror. All right. So, there is another mirror here, and just to show that partially silvered, we have shown it by a patch of yellow. So, there is sun here which gives a light, and this sun, the light comes like this. The light from the sun comes, it gets reflected from this mirror, let us call it as M2, this mirror to be at M1, and then it comes back, and then so because this partially silvered, so this part of it goes, and then it comes back as well, okay, and they get collected by a detector, which is an interferometer. So, this is an interferometer. M1 and M2 are two mirrors. Okay. And M is actually a partially silvered mirror. So, a mirror and a partially silvered mirror, the difference is that a partially silvered mirror allows the light to go through it. So, it is like a glass plate, but it also has the ability to reflect, as we see it here. And these are proper mirrors, that is, they do not allow any light to pass through them, it is completely silvered at the back surface, and this is an interferometer which can be a telescope and so on. And this is say beam 1 and this is beam 2, and there is an apparent velocity, relative velocity, which is the velocity of ether is v. We will see that in the calculations, and this is oriented at a 45 degree to the incoming beam. It is important to make these distinctions. So, these two mirrors are perpendicular to each other, M1 and M2 are perpendicular to each other. So, that is the setup that they have used, and so what they have predicted is that if beam 1 is that gets transmitted and gets reflected by mirror again by mirror M1, comes to this mirror M and travels downward towards the interferometer, whereas this light that comes and it goes to the mirror 2 gets reflected, and then that gets transmitted and it comes to the telescope. Now, if there is a relative speed, that is, if there is a in between these things, if there is a this whole thing moves, then there will be interference, because that is from a coherent source, that is from the same source, that is sun, and there will be a change in the fringe pattern, or the crosswire of the telescope would move through a few fringes, and we should be able to detect that movement of the few fringes, and that is to be looked at, and one needs to the fringe pattern needs to be sort of studied. Okay. So, we need to calculate the phase difference between the two, or phase and path difference. I mean, basically the path difference gives rise to the phase difference between beams coming from M1 and M2. So, that is the job that we have at hand, and so there are two things that are important here. They arise: the different path lengths traveled. So, there are different path lengths traveled by light. So, different speeds, of travel for the beams. Due to ether wind. Okay. So, what I mean is that this ether moves, and then there is so this ether wind velocity, which is called as v. Okay. So, basically here it's the one is more important. So, by one what happens is that so the time for the beam 1 to travel from M to M1 and back. Okay. So, it goes from M to M1 and back, and let us call this length as so the stationary length to be say L1, and that is equal to T1 equal to L1 C minus V plus, write it properly, C minus V, and L1 C plus V. So, there are two L1s which are travelled with two different speeds. One is C minus V and C plus V. C is speed of light, of light, and we have defined what v is, that is different speeds of travel, etc. Okay. So, this is 2 c L 1 c square minus v square. So, this is equal to 2 L 1 by c 1 divided by 1 minus v square by c square. Okay. So, that is the time taken. Okay. So, it is clear that the light has an upstream velocity of c minus v and a downstream velocity of c plus v. So, while going it is c minus v and while coming it is c plus v. For beam 2, we need to have a little more clarity on the situation. So, this length is say L 2, and L 1 can be equal to L 2 or L 1 can be different than L 2. So, let us see for what happens for beam 2. So, this is for beam 1. For beam 2, just to remind you that beam 2 travels from this M to M 2 and back. Okay. But here you have to understand that by the time that it comes back getting reflected from the mirror 2, M itself has shifted by a distance, and that has to be taken into account. So, what I mean is the following, that this is M 2 and this was M earlier, and at a later time when this thing happens. So, there is a reflection that has happened here, and that will give rise to thing here. Okay. So, this is that once again just to make things. So, we use a highlighter, and so this yellow patch says that it is actually M. Okay. All right. So, this is we are here. So, this is again M 2 and this is position M, and this is a later position M, and this is nothing but L 2. Okay. And this is mirror M, and this is this distance that it moves is V T 2 because of this wind speed, or the speed that you have is V T 2. Okay. So, that is there, and this is L 2 and so on. Okay. So, this there is a speed V here. So, the transit time again from M to M 2 and back. So, M to M 2 and back, this transit time is given by C T 2, that is what the speed of light takes in a time T 2, is equal to twice of, is basically the if you consider this as a right angle triangle. So, you are calculating this hypotenuse, and this hypotenuse is L 2 square plus a V T 2 by 2 whole square. Okay. So, that will give you your T 2, and L 2 square is understandable, that is the perpendicular distance, and V T 2 is the horizontal distance, and because it is this V T 2 by 2 whole square, that is the half the distance. So, this distance is V T 2 by 2. All right. So, that gives you T 2 equal to 2 L 2 divided by root over of c square minus v square, and this is equal to 2 L 2 by c, and 1 divided by 1 minus v square by c square. Okay. So, we got T 1 and T 2. Okay. So, T 2 is done in the ether frame, and while T 1 is done in the frame of reference, or rather in the this in the frame of the apparatus. So, this I think is an important thing. So, T 1 is made in frame of apparatus, this setup basically, and T 2 is made, this measurement is made in ether frame. Alright. So, we now have both T1 and T2 and we can find out the difference between the two times. So, which is equal to T2 minus T1, which is equal to 2 over C L2 divided by 1 minus V square by C square and minus L1 divided by 1 minus V square by C square. Of course, there is a difference between the two, which tells that the path length they take different times to travel, and then the path lengths are of course different, and then that will give rise to phase difference, and this phase difference will give rise to an interference pattern to the crosswire to shift from one fringe to another. Okay. Now, what you do is that you interchange L1 and L2. So, if you do that, that is, you make these lengths to be completely different, or rather what you do is that you rotate the apparatus by 90 degree. So, if you do that, let us call that as delta t prime, which is equal to T2 prime minus T1 prime, and then this becomes equal to L2 divided by 1 minus V square by C square minus L1 divided by root over of 1 minus V square by C square. So, that is the change that you have. So, now if you calculate a delta t prime minus a delta t, in experiments it is easy to change the lengths, because that is where you keep the mirrors, so this is equal to 2 over C, and you have a L1 plus L2 divided by 1 minus V square by C square, and a minus of L1 plus L2 divided by root over 1 minus V square by C square. So, that is the change in time. If you do a binomial expansion for V by C to be smaller than 1, do the expansion, and then one gets the delta t prime minus delta t, that is equal to 2 over C2 L1 plus L2 and 1 plus V by C square. So, we do it for both the terms, 1 plus V by C square for the first term, and 1 again 1 minus half V square by C square. Okay. And this gives you L1 plus L2 by C V square by C square. Okay. So, this rotation of the apparatus by 90 degree should cause a shift in the fringe position. Okay. And because that changes the phase relationship between the two beams coming from M1 and M2 in these two. So, the optical path length difference between the beams changes by one wavelength of light. So, if the optical this thing changes, then there will be a shift of one fringe, shift of one fringe at the crosswire. I think all of you are familiar with this crosswire, because this is where you see that there is a plus type of thing there, which tells you that that probably is there either in the middle of a minima or a maxima, and by whatever it is, it gets shifted by certain few fringes maybe. Okay. So, if delta n, that is the fringe shift or number of fringes shift, this is a fringe shift, then delta n is given by delta t minus delta t prime, delta t prime minus delta t divided by t, where t is equal to the time period of one vibration. So, that is lambda by c, where lambda is the wavelength of light and c is the speed. So, this is nothing but equal to like 1 over n or 1 over the frequency and so on. Okay. So, this is equal to L1 plus L2 by Ct and V square by C square, and this is equal to L1 plus L2 by putting t equal to lambda by C. So, this is lambda and a V square by C square. Okay. So, in the experiment, in actual experiment, so they have kept these lengths to be same, and they are 22 meters. They have used the wavelength of light to be 5.5 into 10 to the power minus 7 meters, and V by C is taken as 10 to the power minus 4. That is the like the speed of ether. Then delta n should come out to be, if you put in all these values, it should come out to be 0.4. So, this fringe shift should have been observed. And unfortunately, nothing was observed there. Okay. So, and there was no observation of such things, and it was in fact they for the accuracy of the experiment, they mounted it on a massive stone to eliminate any vibration, other kind of vibration which otherwise would have affected the experiment, and then they have mounted it on mercury so that it can be smoothly rotated, but nothing gave rise to any fringe shift. And this experiment has been done by a number of people, number of groups, and they have been carried on for about 50 years, around 50 years, and at different in different seasons, so that whether this ether wind has any effect on whether you are experiencing winter or summer, or in fact day and nights, whether the rotation of the earth, that is coming into the picture, but there is no absolutely no change in the in the fringe shift that is observed through this experiment. And later in 1958, Sederholm and Towns, they carried out an ether wind experiment using microwaves, not using light, but microwave with a different frequency, and concluded that if this ether theory to be correct, the Earth's orbital speed through ether would have to be 1000 times less, which means that all these Earth's rotation and revolution that gives rise to day and night and different seasons, they would be completely destroyed by this theory. So, which means that finally it is proved beyond doubt that there is nothing called ether, and its light actually does not require any material medium to propagate from one point to another. And it also tells us that there is no frame of reference that is preferred. So, all frame of references are equivalent, and this is one of the upshots of, or one of the headlines of, the special theory of relativity. Okay. So, let us write down the postulates of special theory of relativity. And these postulates are laws of physics, are identical, that is, they are invariant in all inertial systems. there is no special inertial system. So, the all are equivalent, which is what I just said. And speed of light has same value in all inertial systems, and irrespective of the direction in which its light is propagating. So, these are so we can really talk about relative motion of two frames, and there is no way to infer, or rather no way to say for sure that the motion of an absolute or there is no notion of absolute motion or absolute rest, and that probably justifies the name relativity. Okay. And of course, we have seen that Galilean relativity or this transformation equations, they break down, and we need to have new transformation equations which would make these laws, such as the laws of mechanics and the laws of electrodynamics, to be invariant. And so, we need transformation equations. I am not saying of what, but they belong to everything: velocity, distance, and if time is not the same again, and then there needs to be a transformation equation for time as well, and these are important to get. So, transformations equating various quantities are needed, because we had to discard the Galilean transformation equations, and these are called as the low range transformation equations. So, we will just do low range transformation equations and stop with this relativity, discussion of relativity. So, these are basically the consequence of Einstein's postulates. And let us call it a relativity of time. Okay. And in particular, what you would be more familiar with is called as a time dilation. Okay. So, let us have a mirror like this. Okay. Let us call it M, and you have A and B are. So, light goes like this and comes like this, and so on, and this length is L0. We will tell you what we are drawing and so on. So, light flash A and detector B. So, these are the two things that we have. So, they are at a small distance apart. So, there is a small distance. All right. So, the distance is shown between this A and B, and the mirror is L0. So, a light pulse from A is sent towards M, the mirror, gets reflected, and it is registered by this detector B. Okay. So, the hands of the clock by that time move by a distance so, this moves by a distance which is given by a delta T 0, which is equal to 2 L 0 divided by C, and we neglect any lateral motion of the light beam. Okay. So, this is equal to delta T 0 equal to 2 L 0. So, this is the time interval that the clock is at rest with respect to the observer. Okay. So, now consider two observers. And let us call them as O and O prime. Okay. So, whose O is at rest in ground, okay, and whose O prime is moves with speed u with respect to O, and again is just a velocity, but we have simplified it that it can move only in along one axis. So, that is the observer, okay. And both O and O prime carry their own clocks. So, let us see what happens. So, in O's frame of reference, of O, and O sees O prime. So, what happens is that, so there is this A and there is the mirror which is B, and this is the one that it moves through. So, so this is the picture that O sees for O prime. Okay. So, this is L 0. So, there is a light flash that is sent to the mirror, and the mirror reflects it, and it is obtained at, or rather this detected by the detector at C. So, this happens in the in O's case or O prime's case as seen by O. Okay. So, there is a sequence of events. Okay. So, the sequence of events is that flash of light is emitted from A, gets reflected from B, and then it gets detected by C. So, in this time interval, let us call it delta t, and this is this is u delta t. Okay. So, in this time interval, delta t, O observes O prime's clock to move by u delta t. So, this the u delta t is the clock that has moved by this distance in space, which is what O registers about O prime. Okay. So, what does O conclude? So, that observer concludes light beam travels a distance 2L where L is given by L 0 square plus u delta t by 2 square. Again the same thing, split it into two right angle triangle and calculate the length of the hypotenuse, the two of them. I mean that is why it is 2 L, okay, and where L is given by that. Okay. So, the time interval measured by O is delta t, this is equal to 2 L over C, which is equal to 2 into L 0 square plus u delta t by 2 whole square divided by C. Okay. So, that is the time interval between these two events of flashing a light and then detecting it. So, this is the time interval that O registers. And if you go to this and call this as equation 1 and maybe this as equation say 2 and this as equation 3. So, if you put 1 in 3, basically you eliminate L 0. So, if you do that, then delta t becomes equal to delta t 0 divided by root over of 1 minus u square by c square, and this is let us call it as equation 4, and this is called as a time dilation. Okay. So, this is an important concept in relativity called as the time dilation. So, O measures longer time interval for the clock of O prime. Okay. So, which means that the moving clock actually runs slow. Okay. So, if there is an occurrence of an event for a time delta t naught, delta t naught is the time that is noted for this event to take place in the frame of O prime, okay, which is moving along with the speed u as compared to the observer O. So, the beginning and the end they take place at the same point in space according to O prime, but not with respect to the observer O. So, that means that the observer O moving with respect to O prime, or rather if O prime is considered to be at rest, then the observer O is moving with respect to him. So, he measures a longer time interval than the proper time delta t 0. So, delta t 0 is called as the proper time and delta t is the longer time. So, moving clocks actually run slow. Okay. Let me do the other thing, that is length contraction. So, we will call it as a relativity of length. Length contraction. Now, we make one important adjustment here, is now the light flash emitted by O prime is in the direction of motion. See, here we have done it perpendicular to the direction of motion. Okay. And now it is in the direction of motion, which means that O, the observer at O, which is at rest, will see that the clock itself has a length. Okay. So, you can think of it like this, that this is the so this is A, and there is a mirror which is like this, and this whole thing has a length L. So, the clock has a length L in O's reference frame. Again, in we are showing thing in frame of reference of O. Okay. So, now what happens is that there is a light pulse that is emitted, and we see that in B's reference, or rather this O prime. So, that is like this, and then there is a so the clock is actually represented by that there is a flash, and the flash is now releasing a signal, or a light flash is being released, and that gets reflected by a mirror, which is exactly what we did. So, this is at a later time. So, this is we can. So, this initial clock will make this thing clear. So, this L plus U delta T1 is this entire length, okay, that is there, and this is, so these all O primes, but these are O prime, but they are actually seen in the frame of reference of O. Okay. So, this distance is L minus U delta T2, and this L plus delta U delta T1, and so this is basically the initial clock, and this is the final clock. And now the motion takes place, or this emission of this light flash takes place along the direction of motion. Okay. So, this light goes and here and then gets detected and so on. Okay. So, this is the detector, which is what we have called as A, B and C. So, A, B and C, that is here. So, this is like A, and so this is like a B, and then this is again like or you can call the B to be somewhere at the intermediate regime, and this call this as C. All right. So, maybe if we will just, all right. So, according to O, the length of the clock is L. Okay. So, O sees O prime's clock having a length L. Okay. So, this length, as we will see, is different than the proper length. So, a light flash is emitted from A, it reaches the mirror at B. So, this is B, and at a time delta T1 later, and in this time interval light has travelled a distance which is C delta T1, which is equal to the length L of the clock plus this additional distance that is L plus C delta T1, and as seen by the observer at O. Okay. So, the mirror moves forward in this interval, and we have a C delta T1 is equal to L plus U, this U delta T1 as well. So, the flash of light that travels from the mirror to the detector in time delta T2. So, this is that delta T2 from the mirror to the detector. So, this is the mirror to the detector back. So, this C is the position of the detector, and so your C delta T2 is now equal to L minus U delta T2. Okay. So, if you solve for equation 1 and 2, which is fairly simple to do. So, we will solve for delta T1 delta T, which is equal to delta T1 plus delta T2. which is equal to L divided by C minus U plus L divided by C plus U. This is equal to 2L by C and 1 divided by 1 minus U square by C square. So, all these things were happening. So, all this diagram may be a little confusing, but this, if you think that this B was actually in a perpendicular direction earlier, and if it is moving in the same direction, O sees that the clock itself has a length, and which is what is denoted by this box, okay. And then it is again detected after it gets reflected, is detected by the detector, and because O sees the length to be still there, maybe a different length. This is what we are going to find out. So, that is why the two boxes have different extensions, and then these light is again detected by the detector, or the flash of light is detected by the detector when it comes from that or reflected from that mirror and reaches C, okay. And all these lengths etc. are shown in the figure itself. And now we are calculating the time that C delta T1. So, within time interval delta T1, light travels this distance C into delta T1, which is nothing but L plus U delta T1. L is the initial length of the clock that is seen by O, that is O prime's clock that is seen by O. So, these are delta T1, and delta T2 is the time within which the light gets reflected from the mirror and reaches the detector. So, this is equal to that, and if you do a bit of simplification here, or rather if you write this delta T as delta T0 divided by 1 minus U square by C square, this is equal to 2 L0 by C. This is what we are using the time dilation formula. So, this is equal to 2 L0 by C, 1 divided by 1 minus U square by C square. So, L becomes equal to L0 divided by 1 minus U square by C square, and this is called as the length contraction. Okay. So, the observer O prime, which is at rest with respect to the object, measures a proper length which is L0. So, this is called as a proper length, just like proper time or true length, or it is also called as a rest length. Okay. So, all observers who are in motion with respect to O prime, because O prime is in motion with respect to O, which means that with respect to O prime, O is in motion. So, all the observers who are in motion with respect to O prime, the primed observer, they would measure a shorter length. Okay. So, this length is contract. So, I write once again. So, moving sticks are shorter. This is called as length contraction and time dilation, and using this one can formulate the equations for the transformation of velocities and transformation of the acceleration etc., from where one can formulate the equations of motion, and by looking at how the electric field and the magnetic fields transform under these length and time, one can also formulate the Maxwell's equations, which are equations for the electromagnetism, which we study in electromagnetism. So, and they are found to be absolutely correct. So, even if Newton's laws fall short in the velocity regime where v is comparable to that of c, the electromagnetic laws or the Maxwell's equation are invariant. Okay. So, we stop here for today, and then we will carry on with more information about early quantum theory and the development of quantum mechanics in the next lecture. Thank you.